Hello, my name is John Scotto, and we'll be going over the ME 498 progress report. Below is the fellow teammates. Ethan Myers, who's in charge of the CAD design, myself, who's in charge of funding, Taylor B., who is the project manager and the fabricator, and Cole, who's in charge of the research behind the project. In this slide, this is the preliminary design ideas, where we had different methodologies and brainstorming sessions reviewing our certain concept designs in order to figure out how we were going to create this trailer. And this top left image is my personal design, where I figured we would use an ag trailer or a John boat trailer, and we can put a hay elevator on the trailer itself. And in this image, we can see how there's um, there's a hitch that you can connect onto a tractor or a truck, and you can alternate the trailer to the side so it could be in field position and home position. And then when you're in the field position, as it's moving along in the field, this trailer is able to pick up the bales, and there's a hay conveyor on the right-hand side of the trailer that picks up the bales. On the left, on the image to the right, we have Taylor B's design, where he wanted to come up, he wanted to follow the same implementation that New Holland created on their stack cruiser. In this image on the bottom right of the slide, we can see the New Holland stack cruiser where they come up to bales, they pick them up, and they follow a hay elevator design. It goes behind the machine and then it stacks it, and it follows has these fingers that follow the elevator all the way to the back and stacks the bales. And Taylor figured that'd be a positive design, something for us to go off of. That could be great. On the image on the bottom left is Ethan Meyer's design, where his design consists of three different hay elevators. And he figured the way that these bales can go onto the machine and stack, it'd be it'd be beneficial for the consumer using this type of design. And Cole's image is on this bottom right, and his image follows the constraints of using a hay elevator. And we thought this was a perfect execution of how we can pick up the bales. And his main focus was making sure that the bales don't break when they go on the trailer.
All right, our design. From the CAD perspective, this is our fifth iteration and our simplest one. So for a project management perspective, this is our best design. It is two hay elevators that essentially form one collapsible one. The top one slides along the top one and then pivots at the end so that it can rotate down and touch the ground, while the bottom one remains flat with the trailer. At the front end of the top one, there are a bunch of rollers with some rubber wheels, and those wheels spin real fast, and when it makes contact with a square hay bale, it lifts it up and onto the rollers, and then onto the hay elevator, which brings it to the lower hay elevator, and then drops down, slides down a sheet metal ramp into the rollers. You can theoretically fit about 3 in there before they start rolling out the back. We're not going to, set a record or anything. We're just trying to prove that you can take multiple, and it's more about the intake system and the hay elevator that we're interested in at this point. So, our intake wheels. There are 5-inch Big Master Car rubber intake wheels. On the outside of their shafts are some just leveling wheels that essentially keep the rest of the wheels from touching the ground, and so they don't just rub off the dirt or whatever. So the trailer can actually roll along with the intake wheels running. So the outside wheels are just a little bit larger, but it's the same material. We've opted to go for like the lowest durometer rating possible with these wheels. So that means they'll be softer, which is better for this very squishy material that we're using, which is hay. And I'll explain a little bit more about that in the next slide. Another advantage of this design is that we used a single drive motor for everything. We used a pulley to get to from the DC motor to, it'll be about a 3/4 horsepower DC motor. We used a pulley to get that down about, if I remember correctly, 18-to-1 ratio or something, to a smaller shaft, which is the hay elevator shaft, so it'll be going slower, but with more um, oomph or torque. Um, and meanwhile, there'll be another one straight from the motor, which will be running at about 18,000 RPM to the intake wheels, so we get the hay up and over easy, and then it slides on some intermediate wheels, which you can kind of see there, which are just freewheeling like the outside wheels that roll along the ground, just to get it onto the chain easier without it bumping into something. Another interesting part of this design is we added counterweight springs. So depending on what material we use, we haven't nailed it down yet. It'll be a lot easier to put it back into its compact configuration if you don't have to fight the weight of the motor, the rollers, and if we use steel, all that steel tubing. The final advantage of this design that we are excited about is that because of those springs and just the way that this is set up compared to the last ones, the weight requirements, I mean the strength requirements are dependent also on the material weight. So in essence, that means if we make the whole thing out of steel, it needs to be strong enough to hold up all that steel hanging off the end. But if we make it out of wood, it only needs to be strong enough to hold up all that wood plus the motor and wheels. So that'll be a good prototyping phase or a good intermediate phase. Save us some funding. Okay, so safety factor. It is difficult to get good models by hand out of this trailer because it's so complex. It would be a lot of statics work, and with any collision, especially with the hollow tubes, we're getting into a lot of math that is very easy to do with, since it's already modeled, we're going to just do it in Fusion 360's integrated FEA tab. So what we opted to do instead is we picked out a bunch of high probability of failure points in our design, and we just analyzed those individually rather than this whole structure itself at the same time. So we'll first go over the image. So that is a shear moment diagram generated in Python from some calculations in our midterm report. Essentially, on the previous slide, that pin thingy that the top thing slides along, we just figured, a wrist pin would be a fairly easy thing to break, assuming that nothing else crumples, which it probably will before that wrist pin bends, because it's like a 1/2 inch diameter steel rod. But we just investigated and see if it would, and it wouldn't. It would. The safe deformation amount that we came up with was like 1/10 of an inch. It was a very small amount, and it would take a tremendous amount of force and very quickly to bend it like that before it would just slide back into position and effectively negate the impact. As a general rule, with all of these little calculations we did, with the pin being just an example, we just stuck with the number of 3, safety factor of 3, and we'll refine that more in the future if needed. But we feel that is it's acceptable for farm equipment just from looking at the standards, the British Agricultural Trailers paper, and that's also cited in our paper. Okay, so the next two big calculations we did that weren't really stress analysis, basic level stress analysis, were the chain deflection and the torque requirements for the rollers. So these weren't really like, it's not really a safety factor thing, it's more of will it work or not type of deal. So for the chain, there's not really a good CAD model of the chain we're using because it's an ag chain. It's a double wide chain, so imagine like 2 bicycle chains put together, and then every 4 links it has a fork thing that it's maybe not off the top of my head, I remember it being 4. 4 or so, depending on the manufacturer. A square hay bale fits between these forks at a certain spacing, and we could not find a model of the fork itself, and we could not find one of the chain. So we ended up approximating based off of ISO standard chains, and we just assumed that the fork wouldn't add any structural improvements, which it shouldn't. So knowing that, we modeled it as essentially the wrist pins and linkages, knowing the thickness of the linkages and that there's 4 on each wrist pin. We came up with a number of the how much the chain would deflect, and by that means like in the center, if you put a hay bale and you know how long the hay bale is, like what is the maximum deflection along the center of the chain we can get with a centralized position of the hay bale, knowing that those corners are the only thing that's going to be really pushing it down. And it came out to be just a few inches, which for a 5-foot section is negligible. And in our design prior, we had a chain guide anyway that would lower that figure on additionally. But after doing these calculations, we think we don't need that chain guide anymore, which is pretty neat. Also, like with that 3-inch deflection, that also corresponds to like the chain and total stretching. It remained well within the with a 3-inch down deflection that is just even less so of like a total chain stretch, and therefore it was well within the acceptable elastic tolerances of the chain. And finally, the last big calculation we did was the torque requirements for the rollers. So we were curious, like, will the rollers actually, like, when you bump into the hay bale at very low speeds, will it actually get it up and over the wheels, or will they just like push the hay bale along? And so the way we calculated that is we knew how many rollers will be contacting it, which is 4. We knew how big the rollers are, which is 5 inches in diameter. We knew the width of each of those rollers, which off the top of my head is about an inch and some. And from there, we also knew the durometer of the wheels that we picked out, which I think was 40A. And going to the engineering toolbox, we could get some numbers for like what that would get like in a coefficient of friction. And then we also found a paper that did some research on different different hay products and their coefficients of friction against different materials. And the slickest possible number we found, just for the maximum factor of safety we could, was alfalfa in an extremely wet condition against steel. And we just went with that, just for the maximum, like, worst possible scenario. What does it take to get that hay bale up and over those rollers? And it turned out to be well within the output of our motor running at 18,000 RPM across those 4 wheels.
Moving on to the adherence of codes and standards, the portion of this report, or this portion of the report, is to make sure that we were able to ensure reliability, safety, and compliance with the legal laws and the rules set forth by the jurisdictions, such as the Federal Motor Vehicle Safety Federation, as well as the Washington DOT, Department of Transportation. So in this report, though, and in this project, we took into consideration 2 standards. One of them is the ASABE standards, which is the Agricultural Society of America, and they essentially have jurisdiction over, or they set forth standards for agricultural equipment to ensure their safety, such as load limits, setting up like specifications for braking systems, electronic braking systems for heavier trailers, and also just general safety requirements for allowing these trailers and agricultural equipment to travel on the road safely. In addition to this, we also looked at the FMVSS compliance. This is the Federal Motor Vehicle Safety Commission. So essentially, they're the ones that set up the actual laws that we have to adhere to when we're traveling on federal roads, such as I-5. So they're the ones that set a lot of the standards, like putting fenders, reflectors, setting specific kinds of tires with specific like plies, like a 12-ply tire or 8-ply tire. So those are two different bodies or entities that we needed to take into consideration to make sure that we maintain the overall structural integrity of the trailer and safe operation for both the farm and road conditions. So taking a look at our timeline for this project, we can see in front of us that we have our Gantt chart for our long range project, and we can see that we're still really early in this project, so we don't really have a lot to necessarily show physically as far as things we bought. However, we have just reached our design finalization. As you can see, by now we should have already have a materials takeoffs and be ready, be setting up or be finishing our material orders. We have not reached a step because there have been delays in our design, such as come up with an actual finalization of the design, determining the right way to approach funding and how to actually secure funding, and then also coming up with like ways we actually want to design the trailer, like ways to think about the design and ways to think about how it should be used. So just different ways of thinking about the project has kind of caught delays, but not in a bad way. It's just helped us really reaffirm our alignment of where we want the trailer to be.
Hi, I'm Cole Tinsley, and I'll be in charge of presenting the challenges and solutions that we came up with during this part of our design process. Some of the challenges that we identified included the weight of the parts of our design, the costs associated, the complexity of our design overall, and funding. Some of the problems that we ran into with weight didn't really have to do with what our trailer could support, but rather what our designing means could support in manufacturing and getting it actually together. For example, the full-sized rollers for if we were to do a full-size trailer would have been much heavier. Lining them up would have taken a lot more work. The cage, for example, where we would just bring all of the hay onto the trailer and then the cage would keep it within. That would be a lot of weight that we would have to get onto the trailer and move and maneuver around and get set up, which would have increased the difficulty of producing our design. The complexity of the costs. Again, talking about costs, we have a lot of material that would have been associated with the rollers and the cage and stuff like that. And talking about the cost, we can also talk about the complexity, because the more complex, for instance, our original designs all had to do with stacking the hay. They all had a component of that, and that would have added a lot to the complexity of what we needed to do. More, for instance, more elevators or stacking mechanisms. One design had flippers, which would have, again, more costs, more weight. It would have increased the difficulty of actualizing our design. For funding, we're mostly pretty much entirely self-funded right now because we don't quite have the sponsors that we need to complete a lot of what we need to do. So we've been trying to come up with ideas to work on that. Some of the associated results of having these challenges were kind of delays on working on our report for this midterm, as well as not quite working together all the way. So what we decided to do was meet together, have a design meeting where we decided exactly what we're going to do for a design. But the solutions, generally, the most important thing was downsizing the overall design and what we wanted to do for this project, because getting the working parts for the full-size trailer would have been too difficult. So reducing the size and the scope, kind of having to do with that complexity, narrowing it down to what we wanted to show in our design, working and actually functioning, kind of reducing that stacking function to just getting it on and bringing it back using the roller system that we designed and we thought was worth looking into further. For funding, we decided, Scotto, I think, was working on a brochure to show some local farming people and communities and stuff, connections that he has and that other people have, so that we can try to secure funding for the rest of our project. The solution overall with the meeting was to collaboratively work on a design together and see what works best for what we need to do. In terms of actually using that funding, kind of allocating most of our resource to getting a hay trailer built and, situated, and that roller design, which will be mostly fabricated by us.
For the conclusion slide, so our main goal is to set out and build the self-loading hay trailer. We want to fulfill a need in the consolidating of farm. We want to be able to consolidate the farm market and fill to a growing hay export industry. And the evolution of the designs from arm and walking floor to elevator and the dump bed. So essentially, for the next step of the project, we want to make sure that we get out and build the trailer